The fifth and final module in the section on electric current is 25.5, and it relates to current density. Current density is a more sophisticated concept than just the concept of current. It's how dense the current is at a given point. We can define current density J as the current I divided by the area. And if I think about an object through which current is flowing, for example, if I have a large area, try to draw a square end to that. So I have a large area here. You can see that the current density, as the current is flowing into here, is not as great as if I had a very, very small area. So the current, which is the amps per square meter that's flowing here, in fact, is an important concept with some of the more sophisticated equations in electromagnetic theory. This is the definition. So you have to remember the definition of current density. And it turns out that this current density, J, can also be related to the number of electrons that you have flowing, or charges Q, times their velocity. So this is a second way of looking at current density. Current is a charge that's moving at a velocity v, and if I have n of them, it turns out that this is an equivalent equation, although I'm not going to derive that. It is possible to rewrite Ohm's law in a more sophisticated way that says the current density at a given point, J, is equal to the conductivity times the electric field. And this is actually a vector, and this is actually a vector. So this is a rather sophisticated equation that's sometimes used to connect the electric field that exists in an object with the current density J that's flowing, and sigma, which is the conductivity of the substance. This is conductivity. And you can see why that's true, because if this conductivity is large for a given electric field, it means that more electrical current density is the current density is going to be greater or higher. And remember, electric field is a vector, so this current density is a vector. It's flowing in a particular way. There's a proof here in the notes. We can begin with V is equal to IR, or I times the resistance, which is rho L over A. Then I can take that A and divide it into I, that's I over A. And when I do that, you can see that I get I over A, which is J by definition from right here, and I'm left with L over sigma. I'm left with rho L over A, which is L over sigma, and so then I get this final formula, which J is equal to sigma times V over L, and V over L, the voltage divided by the length, is the electric field. Now that comes from that formula, you'll recall, where the change in the voltage over the change in the distance, is going to be equal to the electric field. You remember that formula that we used previously. And so that connects those in a very interesting way. And this current density is a more general concept. It can be looked at as for example, let's imagine you had a bunch of cats. My cat drawing is not too hot. Little ear. And we've got some positively charged cats. We've got some other ones that are maybe positively charged. Some are negatively charged. And they're running around in different directions. So we could look at all of these charges that were in space and compute the current density. Whereas it's very difficult to think about just an electric current flowing. So this concept of the current density is much more sophisticated, because in any volume of space that we might look at, we can say, oh, in this volume of space, what are the current densities at different points as the current flows from one place to another? And that can be almost like a fluid that's flowing in here, and that is exactly correct. It's a good analogy to think of this almost like a fluid that flows, and it can have different velocities at different points in space. So the current density is defined as the current in amps divided by the square meters of area that it's going through. It has an Ohm's law equivalence using conductivity and the electric field rather than voltage. And we did the derivation of it right here. And it's a more powerful concept, and it can also be related to the number of charges times the charge of each one times the voltage.